An object from another star is slicing through our solar system and doing something we didn't expect. Around 3I Atlas, images hint at a tail that seems to push back on the solar wind, as if space itself bent for a moment. Is it a trick of light, strange plasma physics, or a brand new kind of comet behaviour? Tonight, we dive into the puzzle. Imagine looking up at a sky full of familiar motions, the planets pacing along the eclipse, the slow crawl of long-period comets we've catalogued for generations, and then noticing a speck that simply doesn't play by those rules. That is how the story of 3I Atlas begins. A faint, stubbornly fast point of light caught by an automated survey that excels at finding small, sneaky things. The software flagged it, the humans double-checked it, and almost immediately the data started whispering the word that makes astronomers sit bolt upright: interstellar. At first it looked like countless other discoveries. A tiny streak, barely brighter than the background grain of the universe, reported, time-stamped and posted for follow-up. But the follow-up changed everything. Observatories across the world, professional and amateur, nudged their telescopes toward the coordinates. They took more images. They linked those images to the first set. With each night of measurements, the path became crisper, like tracing over a pencil sketch until the lines can't be ignored. The orbit solution refused to settle into the comfortable ellipse that would mean just another comet. Instead, the math said something simple and shocking at once. This object isn't bound to the sun. It came from out there, and it will go back out there. That's the I in its name, interstellar. It's a tag we've used so rarely that every new one forces us to rethink what ordinary means. Before 3I Atlas, there were two famous visitors: the cigar-shaped oddball that tumbled through with no coma, and the dusty bluer comet that put on a more familiar show but still kept its passport from another system. 3I Atlas arrives with its own personality. Even in the earliest images, it wasn't just a point. There were hints of activity, a puff of brightness that suggested ice is waking up, gases uncorking, dust being lifted by sunlight after an unthinkably long sleep between stars. Interstellar objects don't take the leisurely looping tours we expect from comets born in our outer cloud. They plunge in on a hyperbolic path faster than anything the sun can leash, brush past, and then they vanish into the dark again. That alone tells us a lot. It tells us 3I Atlas must have been thrown out of its home system long ago, likely during the chaotic years of planet formation, when migrating giants and swarms of planetesimals played a cosmic game of billiards. Most pieces land back in their home star's backyard. A few get lucky, or unlucky, and are flung into the galaxy. 3I Atlas is one of those wanderers, finally intersecting our patch of space at just the right moment for our relatively new all-sky watchers to notice. Picture the Discovery team seeing the orbital fit tighten and the numbers refusing to budge toward normal. There's a particular kind of excitement in astronomy that mixes awe with paperwork. You confirm the trajectory, you alert the Minor Planet Center, you scramble for more observations to reduce the uncertainties, you ask for radar if the geometry allows, you chase spectra to find chemical fingerprints in that faint, fuzzy light. The community pivots fast because with interstellar guests you don't get a second chance. The object is always either coming or going. As more telescopes join the chase, a portrait began to form, not just where 3I Atlas was headed, but what it might be. Activity means ices. Ices mean a surface or near-surface layer that can sublimate when warmed. That makes it feel familiar, like a comet from our own deep freeze. But familiarity can be deceptive. Comet-like doesn't guarantee solar system-like. The building materials and temperature history in another star's nursery can create different blends of volatile ices and dust. The colour can shift. The grain sizes can surprise us. The way the coma expands and the tail assembles itself in sunlight can carry fingerprints of a different origin story. There's a human side to all of this too. Behind every crisp plot of an orbit is a person racing the clock under an actual sky, opening the dome before twilight fades, negotiating thin clouds, focusing the optics, taking exposures in quick succession, and then blinking the frames to see if a dot jumps as expected. When the dot doesn't just jump but sprints, when the residuals line up for a path that can't be held by the sun, the air in that control room changes. Voices get quiet, fingers move faster. You can feel the tide of curiosity rising because this is what astronomers live for. A small piece of reality that forces the universe to tell another secret. 3i Atlas carries a second gift: context. With each interstellar visitor, the sample size grows, and with it our ability to compare. One earlier wanderer seemed to be a dry shard, strangely shaped and tumbling as if the outer layers had been baked or blown away sometime in its past. Another looked like a normal comet at first, but had details, grain sizes, gas ratios that didn't quite match our neighbourhood. 3i Atlas adds to that chorus. Does it outgas strongly far from the sun, hinting at unusually volatile ices? Does its light curve brighten and dim in a rhythm that suggests a stretched or oddly proportioned body? Do we see jets, arcs, or a fan? Signs of uneven activity that might point to a patchwork surface? Even the direction of approach has a story to tell. Interstellar space is an empty stillness. It's threaded with the motion of the sun around the galaxy and peppered with the random velocities of the things we meet along the way. The incoming vector of 3i Atlas, where in the sky it appeared and how it crossed the plane of our planets, can hint at whether it belongs to a broader background flow of ejected debris, or if it's a loner with a history all its own. We look for clustering in arrival directions and speeds, the way you might notice that most leaves in a stream drift from a certain bend upstream. If patterns emerge, they could trace back to common processes in planet-forming disks, or even to star-forming regions we can still point to. The name itself is a little poem. 3 marks it as the third of its kind recognised by our species. I is the badge of interstellar citizenship. Atlas nods to the vigilant survey that found it, a network of telescopes tirelessly scanning the skies for anything that moves where it shouldn't, from harmless comets to hazardous asteroids. There's a quiet triumph in that, because the tools we built to protect the Earth also let us greet visitors from beyond the heliosphere with more than curiosity. They let us measure, compare and learn. From the moment 3i Atlas was confirmed as unbound, the clock started ticking. The inbound leg offers one set of opportunities: colder temperatures, fainter coma, subtle clues about the very first wisps of activity. Nearer to the sun, we get brighter signals, richer spectra, and fast-changing structures in the tail. After perihelion, the turn around the sun, we watch how the activity ebbs, whether the nucleus survives intact, whether new jets turn on as sunlight angles change. Each phase is a page in a short book we have to read in real time, miss a page, and it's gone forever. Why does a single small object matter this much? Because 3i Atlas isn't just a comet. It's a messenger. It left another star's gravitational embrace with the ingredients and scars of its birthplace intact. It wandered through the interstellar medium, soaking up cosmic rays and micro-collisions, maybe losing layers, maybe crusting over. Now it's tasting our sunlight and our solar wind, reacting in ways we can see. When we decode that reaction, we aren't just learning about one rock and ice body. We're sampling the chemistry and physics of a place we may never visit, using a courier that crossed the abyss for us. There is also a deeper, humbling truth. Each time an interstellar object appears, it reminds us that planetary systems aren't insulated islands. They exchange material, they shed it, they send it sailing. The same youthful violence that likely cleared our early solar system cast plenty of our own debris outward, destined to be someone else's 3i Atlas. Somewhere, some night, another set of telescopes could be watching a sliver of our past drift by and wondering about us. So here is our visitor, 3i Atlas. A faint smear in the first images, then a sharpened path on a graph, then a living object with breath and behaviour in the glow of the sun. It doesn't belong to us, but for a brief arc of time, it is ours to study. We will pin down its motion, guess at its shape, sniff out its gases, and log the way it brightens and bends. And as we do, we'll add a new line to the ledger of how worlds are built and broken, one small unbound traveller at a time. Start with the sun, not as a quiet disk in the sky, but as a boiling ocean of plasma. In that ocean, heat and magnetism stir the surface and fling material outward. That outflow is the solar wind, a thin, invisible river of charged particles, mostly electrons and protons, streaming off the sun in every direction. It never stops. It rushes past planets, threads through the gaps between asteroids, and combs the hair of every active comet it meets. It is so constant that space, on large scales, is shaped more by this wind than by emptiness. Because the sun rotates, the wind doesn't fly straight like arrows. It unfurls more like water from a rotating lawn sprinkler, carving a vast spiral pattern into the solar system. Carried with this wind is the sun's magnetic field, stretched and wound into that same spiral. In plasma, the field and the flow cling to each other. The particles tend to slide along the magnetic lanes, and the magnetic lanes are dragged by the flow. Imagine streamers tied to a bicycle wheel. As the wheel turns, the streamers sweep into elegant curves. Space around us is full of those curved magnetic streamers. The wind isn't uniform. There's a slow version that drifts at a few hundred kilometers per second, and a fast version that can roar 2 or 3 times quicker, escaping from open magnetic regions on the sun called coronal holes. On top of that, the sun occasionally belches giant bubbles of plasma known as coronal mass ejections. Those move like storm fronts, pushing and reshaping the quieter wind ahead of them. Where different speeds meet, they pile up and form vast corrugated boundaries, traffic jams in space that can buffet anything in their path. We live inside the bubble. This wind inflates, the heliosphere. Far out beyond the planets, the wind slows and mixes with the thin gas between the stars. But here near the sun, it remains swift and supersonic. Threading through this bubble is a wavy boundary called the heliospheric current sheet, where the magnetic field flips its direction. The sheet ripples like a warped vinyl record, and as the planets move, they pass in and out of its folds. That matters because a comet's ion tail tends to line up with the local magnetic field. As the field changes, the tail can twist and reposition, sometimes dramatically, as if tugged by invisible hands. Now picture an ordinary comet waking up. Ice near its surface warms and turns straight into gas, a process called sublimation. The gas escapes, dragging tiny grains of dust with it. Sunlight pushes on those dust grains and gravity pulls on them, so the dust forms a broad pale tail that curves gently away from the comet's path. That dust tail is mostly a story of light and inertia. The solar wind only nudges it. The gas is a different story. As the fresh neutral molecules stream out, sunlight and energetic electrons quickly strip some of them of the electrons, turning them into ions. Those newborn ions suddenly feel the tug of the sun's magnetic field carried by the wind. They're picked up by the electromagnetic conveyor belt and accelerated away from the sun. That's why the ion tail is typically thin, straight and striated, often glowing in electric blues or greens, from species like CO+ and H2O+. It points not exactly away from the sun, but along the magnetic flow lines that are themselves swept into a spiral. To our eyes, that still looks anti-sunward. But the details of the line can kink, twist, or even seem to angle oddly depending on the local field direction and our viewing geometry. Close to the nucleus, the battle between the expanding coma and the oncoming wind creates a structure. There can be a soft shock upstream where the wind first feels the comet's presence, a region where the magnetic field piles up, and an inner boundary where the field can't easily penetrate the dense coma. None of this requires a solid, permanent magnetic field inside the comet. The flow and the field generate the boundaries through interaction alone. It's a bit like sticking your hand out of a car window. The air shapes itself around your hand into smooth layers and swirls without your hand having any wind of its own. When the wind is calm, the ion tail looks steady. When the wind changes, When a fast stream overtakes a slow one, or when a solar storm rolls through, the tail can respond in minutes to hours. Sometimes a whole section disconnects and snaps away, like a windsock torn by a gust. Spacecraft have caught comets in the act. A shock in the solar wind sweeps past, magnetic lines reconnect and rearrange, and then the old tail is cut off while a new one starts growing immediately. From Earth, that can look like a tail that bends, breaks, or points in an unexpected direction for a while before realigning. There's also a trick of perspective that can fool even careful viewers. Comets often show an anti-tail, a narrow spike that seems to point toward the sun. It isn't fighting the solar wind. It's a sheet of larger dust particles left along the comet's orbital path, and when the Earth crosses the comet's orbital plane, we pierce straight along that sheet, and it appears as a sunward spike. Meanwhile, the real ion tail still points away along the magnetic lanes. Two different tails, two different physics stories, overlapping on the sky can create the impression that the wind itself is bending or being defied. Inside the solar wind, waves ripple and turbulence crackles. Those fluctuations shake charged particles and can steer ions into beams or curtains along the tail. Small changes in the field direction sweep through, and the tail follows, like seaweed aligning with passing wave trains. Sometimes you see striations, distinct rays in the tail, that map these changing conditions. Even without a dramatic solar storm, the ordinary restless texture of the wind leaves fingerprints on a comet's plasma plume. For a visitor like 3I Atlas, all of this becomes even more interesting. The mix of ices and dust determines how quickly the coma builds, which molecules ionize first, and how bright or reactive the ion tail becomes. If the object carries unusually volatile ices that wake up far from the sun, the solar wind encounters an active coma in places where most comets are still asleep. And the balance between wind pressure and outflow can look unfamiliar. If the dust grains charge different, or the gas jets are strongly one-sided, the shapes they carve can momentarily seem to push against the expected flow. Add in our line of sight. Are we looking down the tail from the side or at an angle? And you can assemble scenes that appear to contradict the rulebook even when every particle is obeying it. Another subtlety. The magnetic field direction the tail traces isn't set by a straight line from the sun to the comet. It's set by the spiral and by whatever local twist the wind is carrying that day. A tail that angles a few degrees off anti-sunward isn't misbehaving. It's telling you the field has a certain tilt. A kink that slowly walks along the tail is the signature of a passing wave. A sudden dogleg can be the edge of a solar wind stream to the boundary of the heliospheric current sheet. In that sense, comets are space weather vanes, visible, delicate indicators of invisible winds. When researchers talk about the solar wind sculpting a comet, they're summarizing a whole chain of micro-events. Photons knocking electrons off molecules, ions feeling electric fields, fields being stretched by moving plasma, and the whole messy, beautiful system adjusting itself continuously. No single moving part needs to be exotic for the overall picture to get complex. That's why long monitoring campaigns matter. By watching a comet through changing solar wind conditions, quiet days, fast streams, and storm passages, we can separate geometry from physics and tease out which features belong to the comet and which belong to the wind. All of this is the stage on which the mystery around 3I Atlas plays out. If observers see a feature that seems to lean into the wind, or stand where the wind should sweep it aside, they have to ask, is this dust masquerading as an ion tail? Are we looking along a sheet of particles and misreading depth as direction? Did a magnetic sector boundary just roll through? Is a jet from the nucleus drawing out a persistent streamer that, from our angle, looks rebellious? The solar wind provides both the rules and the red herrings. In the end, understanding the solar wind is like learning a new kind of weather. There are prevailing breezes, trade winds, and sudden squalls. There are tides in the magnetic field and shifting fronts that pass by in invisible majesty. Comets are the windsocks and streamers that reveal that weather to our eyes. When the footage of 3i Atlas shows something that looks impossible, the first step is to read the sky like a meteorologist. Check the background flow, watch for changing sectors, compare the dust and ion behaviour, and remember how perspective can fool us. Only after we've ruled out the familiar tricks of this restless wind should we reach for new physics. Until then, every bend and a brightness is a clue the solar wind is leaving in plain sight. When people say a comet's tail is misbehaving, it usually isn't the comet breaking the rules, it's the rules being more interesting than we first thought. A comet doesn't have one tail, so much as a whole ensemble of structures that light up differently, move on different timescales, and can trick our eyes depending on where we're standing in space. Dust behaves like confetti carried by sunlight and momentum. Ionized gas behaves like silk threads pinned to magnetic lanes in the solar wind. Put those together, give the nucleus a few active jets and a slow tumble, and then view the whole scene from a shifting angle while Earth loops around the sun, and suddenly normal can look outrageous. Start with dust. As a comet warms, gas seeps out and drags grains from the surface. Big grains hardly notice sunlight's push. They lag behind the comet and form a pale, gently curving ribbon along its path. Tiny grains get shoved harder and swing wide into a broad fan. Over days and weeks, these different sizes sort themselves. So a single snapshot actually contains dust of many ages and speeds, layered in depth like veils. The eye flattens all of that into a two-dimensional picture. What should be a soft fan away from the sun can look like a claw, a split fork, or a bright spike that seems to lean the wrong way. That sunward spike has a name among comet chasers, the anti-tail. It isn't a rebellious gas tail fighting the solar wind. It's a sheet of dust that the comet left along its orbit earlier, like sawdust sprinkled along a curved workshop floor. Most of the time that sheet is invisible. But when Earth happens to cross the comet's orbital plane, when our line of sight lies exactly in that thin layer, we peer edge on through the dust and it condenses into a sharp lance that appears to point toward the sun. The comet didn't reverse physics. We just slid into the perfect theatre seat to see a normally hidden set piece. Light itself helps the illusion. Dust grains don't scatter sunlight evenly. They glow more strongly at some angles than others. When the sun, the comet, and Earth line up just so, the dust can flare in brightness. Sometimes that happens when the sun is almost behind the comet from our view, sometimes when it's almost behind us. Either way, the lighting can punch up a faint sheet into a vivid blade. Photographs enhance the drama. Long exposures and image processing pull out delicate low-contrast structures and can make a modest feature look like a bold statement. Change the exposure, and the weird spike melts back into the larger normal fan. Ionized gas tells a faster, sharper story. Freshly minted ions in the coma feel the magnetic field carried by the solar wind, so the ion tail often forms a straight, narrow beam that points roughly away from the sun, but away really means along the local magnetic lane, which can be tilted and curved on large scales. That's why an ion tail can show sudden kinks, S-shapes or steps. A ripple in the wind passes by, the field direction shifts, and the whole tail swivels within minutes or hours. Sometimes a storm front in the wind snaps the old magnetic connection, and the visible tail literally disconnects, floating away while a new tail sprouts from the head. From Earth, that looks like a tail that broke off and regrew, which is exactly what happened, just not with scissors, but with magnetism. Close to the nucleus, the choreography gets intricate. Comets rarely vent evenly. They spritz through jets, patches on the surface where sunlight wakes up buried ices. If the nucleus is rotating, those jets trace spirals in the expanding coma, like a rotating lawn sprinkler throwing arcs of mist. Seen from the side, a spiral projects as a corkscrew. Seen from almost any other angle, it becomes a series of rays and fans that flicker, flare, or even seem to cross one another. Give the nucleus a lumpy shape, add shadows from its own hills and pits, and the on-off blinking of jets can create the impression of structures pushing into places they shouldn't be. There's also the matter of time. Dust is slow drama. A dust fan today includes particles released days or weeks ago, so it smooths over sudden changes and preserves memory. The ion tail is live television. It reacts to the solar wind now. If you compare two images taken an hour apart, the dust may look nearly identical, while the ion tail has sprouted a kink, snapped a piece, or tilted a few degrees. Stack those images to boost the signal, and you can accidentally blend past and present, making the scene look stranger than it truly is. Some of the wildest bends appear when recent razor-straight ion features overlay older, gently curving dust sheets. Perspective is the quiet trickster in all of this. Imagine standing beside a river with two currents, one fast, one slow, flowing in different layers. If you look down from a bridge, you can see them as separate streams. If you crouch at water level, the layers collapse into each other, and eddies appear to run in impossible directions. Space does the same to us. Tilt the orbital plane a few degrees, and the broad dust fan compresses into a blade. Shift Earth a little around the Sun, and we look along the ion tail instead of across it, turning a straight thread into a bright, short stub that seems to end too soon. Even the star field behind the comet can complicate the read. Stacking software aligns on the comet, smearing the stars into streaks that run through the tail and sketch phantom lines where none exist. Sometimes the mischief is baked into the grit itself. Not all dust is the same. Fluffy aggregates, compact grains, and tiny fragments each catch sunlight differently and feel radiation pressure to different degrees. As larger chunks fragment, they release clouds of finer powder that form narrow striations, parallel streaks in the dust tail that look like the ribs of a fan. Those striations aren't wind-carved, they're time-stamped, size-sorted dust lanes laid down by a nucleus that shed material in bursts. From certain angles, these ribs can mimic separate tails competing for direction, one even appearing to lean sunward, while another streams anti-sunward. When observers report a tail that seems to push back on the solar wind, the first suspect is usually mislabeling, dust mistaken for ion, or a dust sheet seen edge on at the perfect moment. The second suspect is a passing boundary in the solar wind that quietly rotated the magnetic field. So the ion tail drew a new line across the sky while the dust fan, unfazed, kept its broader curve. The third suspect sits on the nucleus, a well-aimed jet that emits a persistent streamer at an angle that, from our vantage, looks like a challenge to the wind. Add them together, and a perfectly lawful comet can look like it's rewriting the rules. This is why comet imagers use filters and cadence as their lie detectors. A broadband image shows both dust and gas all at once, beautiful but confusing. Narrow filters can isolate common ion species, turning the ion tail into a crisp separate structure and revealing whether the rebel feature really follows the magnetic lanes. Rapid sequences, images minutes apart, act like a windsock. If the feature wriggles quickly, it's likely ion. If it hardly moves but brightens with changing angle, it's probably dust. For a visitor like 3i Atlas, layering those tricks with careful geometry, tracking the phase angle and orbital plane crossings, can separate spectacle from surprise. None of this means true surprises never happen. Sometimes a comet crosses the heliospheric current sheet, the vast wavy boundary where the sun's magnetic field flips, and the ion tail performs a dramatic dogleg. Sometimes a coronal mass ejection barrels through and scours the coma, reshaping the whole plasma environment in an afternoon. Rarely the nucleus itself sheds a bigger fragment. A secondary mini-coma blooms, and for a while there really are multiple heads with multiple tails pointing at slightly different angles. Even then, the physics stays consistent. The misbehaviour is the system revealing its moving parts. So if footage of 3i Atlas shows a spike towards the sun, think dust sheet and plane crossing before thinking new force. If it shows a hard bend, look for a magnetic sector change. If a piece of the tail detaches and floats away, that's a classic disconnection event. The magnetic rope was cut upstream and a new one is being woven. And if a narrow streamer holds a stubborn angle for days, consider a persistent jet tied to a rotating patch that just happens to paint its beam where our viewing geometry interprets it as defiance. In the end, tails that misbehave are our best teachers. They pull our attention to geometry, to lighting, to the quiet details of how dust is made and broken, to the living weather of the solar wind. Every odd spike or kink is an invitation to read the sky more carefully. If 3I Atlas is caught in one of those moments, appearing to bend the wind or stand against it, the path to understanding starts with the simplest tools. Identify the dust. Isolate the ions. Note the angles. Watch how fast things change. Most of the time, the mischief dissolves into a gorgeous, lawful dance, and if anything remains that truly won't fit, that's when we know we've found something new. The first time people noticed it, it was just a whisper in the data. A set of deep images of 3I Atlas showed a slender feature that didn't quite line up with expectations. It was narrow like an ion tail, bright enough to be real, and yet it leaned ever so slightly toward a direction that just shouldn't have been stable. A few observers chalked it up to processing artifacts. Others pointed out that nearby stars, smeared by the stacking software, could fake a filament. But then more frames arrived from different telescopes, different nights, different skies, and the same odd geometry kept slipping through. A tail that seemed to shrug at the solar wind's command. If you think of the classic picture, it's simple. Dust makes a broad fan that curves, ions make a straight anti-sunward spear. The spear can wiggle because the magnetic field wiggles, but it still points roughly away from the sun along those invisible lanes. What began to bother people about 3I Atlas wasn't a wild break from that rule, it was the persistence of a small defiance. A streamer held an angle that didn't match the magnetic weather reports others were seeing, and it didn't fade the way a trick of perspective usually does as Earth moves. Night after night, within the limits of noisy observations, the contradiction kept turning up as if the comet were politely insisting on its own choreography. The hunt to pin this down became a lesson in how fragile the truth can be in low signal. Teams compared raw and processed frames to rule out sharpening halos and background gradients. They rotated the stacking reference, a line on the stars, a line on the comet, a line on the tail itself, to see what survived. Some groups used narrow filters centered on common ion emissions to isolate the plasma tail from dust glow. Others, lacking those filters, worked with carefully calibrated color composite sets to tease out subtle differences. When a feature persists across methods, you start trusting it. When it fades in one method but not another, you get cautious because the universe is not obligated to be convenient, and image processing is a magician with too many tricks. Geometry took its turn on the Whitman's stand. Was Earth near the comet's orbital plane, the classic setup for a dust anti-tail to look like a sunward spike? People modelled the plane crossing and found that yes, certain dates would favour the illusion, but the timing didn't perfectly track the stubborn streamer. Could a dust sheet plus a modest jet produce a composite that mimicked a bent ion tail? Plausible, especially if the jet came from a patch that rotated into sunlight at just the right hours. Those reconstructions explained parts of the pattern, but not all of it. And the remaining mismatch kept attention fixed on the idea that the wind itself might be getting redirected. To pursue that possibility without jumping to conclusions, observers turned into space weather analysts. They pulled the daily maps that track the solar wind's speed and the direction of the magnetic field threading the inner heliosphere. They marked the position of 3I Atlas against those flows and looked for moments when a sector boundary, where the magnetic field flips, should have swept across the comet. If the streamer were truly an ion structure, it ought to pivot, kink, or even briefly disconnect when the boundary passed. On some nights the tail obliged and performed textbook maneuvers. On other nights the streamer barely blinked, as if it was anchored to something more local than the sprawling magnetic lanes. That inconsistency is where curiosity sharpened into a puzzle. Closer views added texture. High cadence sequences, images taken every few minutes over an hour, revealed a fine sawtooth pattern running along the bright filament, beads and striae that looked like waves moving down a rope. In a standard ion tail, such ripples can be signatures of turbulence and pickup processes, the normal shakiness of plasma caught between outflowing gas and incoming wind. But in 3I Atlas, the ripples sometimes marched at a pace that didn't match the ambient wind speed estimates, and the whole filament seemed to hold its slanted bearing while the ripples slid along it. That's the kind of detail that makes modelers rub their temples. Part of the behaviour says, I'm a normal ion tail, and part says, I'm listening to a different drummer. Meanwhile, the dust refused to be a passive backdrop. Photometry showed a gentle brightening trend that suggested sustained activity rather than sporadic bursts, and the broad fan of dust took on a faint ribbing, parallel lanes likely laid down by changes in the nucleus's spin or by fragmenting grains. Where those ribs crossed the narrow filament, interference patterns popped out in long exposures, little diamonds of light and shadow that teased the eye into seeing bends or joints that weren't really there. Untangling that visual braid required multi-filter imaging, and not every observer had the tools or sky time to do it. The result was a patchwork of partial truths, convincing evidence of a persistent slanted streamer from some teams, and equally convincing demonstrations of dust illusions from others. Into this mix came a handful of spectra. Even low-resolution spectra can separate dust-reflected sunlight from the telltale emissions of common ions, and on the nights with the right equipment, the slanted feature carried faint but real ion signatures. That didn't end the debate, it only deepened it. If the filament was indeed rich in ions, why didn't it obey the prevailing field direction cleanly? A few researchers floated the idea of an induced magnetic bubble around the comet, a region where the solar wind's field piles up and drapes, forcing the flow to swerve. That happens around active comets, it's not exotic. But the degree of swerve implied by the geometry seemed large for the measured level of activity, as if 3I Atlas were punching a bit above its weight. Another clue came from timing. On several nights, observers recorded a faint counterstreamer on the opposite side of the nucleus, a shadowy ray that flickered in and out like a ghost limb. In standard comet behaviour, such opposite rays can be the projected edges of a rotating jet, or the line where outflow meets a local magnetic fold. Here, though, the timing of the ghost ray's appearance sometimes lined up with small changes in the primary streamer's brightness, as if the two were connected through a rotating source. If a jet on the nucleus were strong and narrowly collimated, it could feed ions preferentially into one direction, where they'd then be swept by the field. But if the field were draped and compressed, that preferred direction could be skewed, and from Earth it would present as a steady slanted beam. None of this on its own breaks the model, it stretches it. It asks the model to accommodate a set of boundary conditions we don't often see all at once. An interstellar traveller with possibly unusual volatiles waking up earlier than typical, a moderate but persistent jet, a viewing geometry that amplifies one streamer, and a solar wind in a temperate but not quiet mood. What made the case around 3I Atlas feel like a crack in the familiar picture was that multiple independent observers kept reporting the same stubborn angle under changing space weather conditions. If the wind truly shifted and the streamer did not, either our wind estimates were off at the comet's location, or the comet's local environment was strong enough to resist the shift for longer than expected. That led to a flurry of what-ifs that good science thrives on. What if the ion population being traced wasn't the usual one? Different molecules ionize and radiate under different conditions. A tail bright in one ion might highlight a flow that reacts sluggishly to small field changes. What if large dust grains carried electric charge and, for a while, were shepherding ions along a path that favoured the jet's direction? What if the nucleus's rotation period created a repeating pattern that, when sampled at the same time each night, locked observers into the same phase, fooling us into thinking the streamer's orientation was fixed? Each of these scenarios is testable with the right cadence and filters. To move from speculation to clarity, the community did what it does best: coordinate. Observers in different longitudes set up relay-style coverage to break the same local time curse. Teams with ion-sensitive filters scheduled overlapping windows. People with access to space weather models pushed for simulations that could predict the field direction at the comet's exact position, not just near Earth. A few observatories targeted the coma upstream of the nucleus, looking for the telltale brightening and contours that mark a pileup of magnetic field, a draped sheath that could set a preferred lane for ions. If that sheath had a consistent tilt relative to the Sun-Comet line, it might explain the streamer's loyalty to a particular angle. As data accumulated, a picture began to coalesce that was both satisfying and slightly maddening. On many nights, 3I Atlas acted like any comet. The ion tail traced the local magnetic field. The dust fans swelled and glowed. Kinks and ripples whispered the daily news of the solar wind. On some clusters of nights, however, a narrow enhanced filament hugged a slanted bearing through small changes in the wind's direction, then finally yielded and snapped into a new alignment when a larger shift rolled through. That behaviour suggests thresholds, local structures that can resist nudges but surrender to shoves. In other words, the model remains intact, but it needs to account for a sturdier local scaffolding than we usually bother to include for modestly active comets. If you're waiting for a grand single-sentence resolution, 3I Atlas refuses to give it. The bend that broke the model turned out to be more like a stress test that revealed where the model is thin. It reminded everyone that a comet is not a point with a tail. It's a small, messy atmosphere, its own little world negotiating with a big, messy wind. In that negotiation, jets and geometry can create protected lanes. Magnetic draping can set preferred angles. Different ions can highlight different flows. And our vantage point can amplify or erase all of the above. For storytellers, that might sound less dramatic than a new force or an alien object rewriting physics. For scientists, it's better. It means we've found a regime where careful, well-timed observations can pry open details about how plasma, dust and sunlight conspire to build the beauty we see. It means that by watching 3I Atlas through more sector crossings and wind changes, by catching it at different phases of its spin, by separating ions with different filters and tracking their behaviour over hours instead of single snapshots, we can turn a lingering annoyance into a map of the comet's local environment. And still, there's a tantalising edge. If, after all the corrections and careful watching, a streamer keeps its own counsel through shifts that should move it, then 3I Atlas would be telling us that something about its coma, its chemistry, its charging, its micromagnetism, is stronger or stranger than we expect. That's a discovery worth the late nights, the failed stacks, and the patient comparisons. Because every time one object forces us to add nuance to the simple picture, all the other comets get more interesting too. 3I Atlas may not have broken the model, but it leaned on it hard enough to show us where to rebuild, and that is how a faint smear on a CCD becomes a new chapter in how we understand the wind between the worlds. Imagine the solar wind arriving like a steady breeze and finding not a naked snowball in space, but a soft, expanding atmosphere that pushes back. That is the essence of the magnetic cocoon idea. The outflow of gas from 3I Atlas becomes ionized. Those newborn charged particles load the wind with extra mass, slow it down, and force the sun's magnetic field to drape around the comet. The draped field and slowed flow together create a protective sheath, a kind of induced magnetosphere that redirects the incoming stream. Inside that sheath, the field can even weaken to almost nothing, forming a tiny calm eye amid a storm of charged particles. From far away you don't see the invisible field lines, you see their consequences. Tails that cling to preferred angles, kinks that propagate like ripples on a taut rope, and boundaries that hold their shape longer than you'd expect if the wind was simply blowing straight through. To picture how such a cocoon begins, start at the nucleus. Sunlight warms patches of the surface and gas leaks outward, dragging dust along. At first, those molecules are neutral. They don't care about magnetism. but space is bathed in energetic light and particles that quickly knock electrons off a fraction of that gas, just turning it into ions. The moment ions appear, the solar wind feels the coma in a new way. It has to carry those ions along, and in doing so it loses some of its speed and momentum. The magnetic field embedded in the wind can't just cut through. It piles up and bends around the obstacle like streamers curling around the side mirrors of a moving car. That bending is magnetic draping, and it naturally sets up a direction for charged material to flow around the comet rather than straight through it. If the outgassing is strong enough for long enough, distinct layers form in front of the nucleus along the windward side. First comes a region where the wind begins to slow and the field intensity rises. Farther in, a gentle, shock-like transition can appear, where the character of the flow changes more abruptly. Deeper still, near the nucleus, is a place where the tangled field lines can't easily enter because the dense, expanding gas pushes them aside. An almost field-free pocket, sometimes called a diamagnetic cavity. None of this requires 3I Atlas to carry a permanent bar magnet strength field of its own. The magnetism is induced by the interaction. Think of a boat moving through thick reeds. Even without an engine pushing the reeds aside, the very act of moving and the swirl of water reshapes the plants into a sheath around the hull. Now connect that structure to the bending mystery. If a draped magnetic sheath is tilted relative to the straight Sun-comet line, because of the comet's motion, a strong one-sided jet, or an asymmetry in the coma, the easiest path for newly created ions is along that tilted sheath. They slide down those curved magnetic lanes, and the bright ion streamer we photograph traces the lane it rides. To an observer on Earth, it looks like the comet is holding a tail at a stubborn angle to the wind, but the wind is being diverted. It's skirting the cocoon and carrying the field with it. The apparent defiance is the visible edge of an invisible flow barrier. There are reasons to think an interstellar visitor like 3I Atlas could be especially good at building such a sheath. If its ices include unusually volatile species, it can start outgassing farther from the Sun than most comets, inflating a broad coma earlier. If outgassing is channeled through a persistent jet, say a crack or pit that stays sunlit for long stretches, the coma can be lopsided, feeding more ions into one side and thickening the sheath there. The comet's rotation can then lock in a repeating pattern, refreshing the same funnel of gas each turn and helping the cocoon maintain a preferred orientation, even as the background solar wind drifts a bit. From the outside, what would you see if a magnetic cocoon is at work? First, the narrow ion filament would respond sluggishly to small day-to-day shifts in the solar wind's magnetic direction. Instead of swiveling instantly, it would hold its angle until a stronger push, like a fast stream or a solar storm, overwhelms the local structure. Second, ripples would run down the filament at speeds that reflect the local plasma environment of the sheath, not just the bulk wind. Those ripples can appear as bead-like brightenings that march tailward with a steady cadence. Third, a standoff distance, the gap between the nucleus and the place where the tail seems to really narrow and launch, might remain larger than expected for the overall brightness. That gap can mark the inner boundary of the piled-up field, a visible hint of where the sheath grips the flow. There are also telltale behaviours during space weather events. When a boundary in the Sun's magnetic sectors passes the comet, many comets show a dramatic disconnection. The existing ion tail detaches and floats a while a fresh tail sprouts. With a robust cocoon, the timing of that cut can lag slightly, or the cut line can form along the pre-tilted sheath rather than straight anti-sunward, giving the impression of a tail that breaks on a slant. Later, when the wind fully reconfigures the field around the comet, the new tail might snap to a very different angle in a short span, evidence that the cocoon can resist nudges, but yields to shoves. How could we test this without a spacecraft parked beside 3I Atlas? We lean on remote diagnostics. Narrowband imaging that isolates specific ion emissions lets us trace just the plasma component and ignore dust, revealing whether the stubborn streamer truly belongs to charged gas. High-cadence imaging can measure ripple speeds and look for consistent phase lags after known space weather changes, which are tracked by solar observatories close to the Sun and near Earth. Polarimetry, looking at how light is polarized as it scatters from dust, can map where dust dominates versus where ions do, helping us see whether the bright lane is a plasma highway cutting across a wider dust field. Even low-resolution spectra can compare the relative strengths of different ion species, some of which may prefer slightly different paths depending on how the sheath shapes electric fields near the comet. Modelers can add another layer. Computer simulations that inject a realistic outgassing pattern, patchy jets, rotation, and a guessed mix of volatiles into a flowing solar wind can produce a draped field and a sheath. By nudging the background wind and rotating the comet in the model, you can see whether the synthetic tail holds a tilt for the same range of conditions observers report. If the model needs only modest tweaks to match the data, the cocoon hypothesis gains weight. If it requires extreme outgassing, or an unrealistically strong sheath for the observed brightness, the idea needs revisiting. A magnetic cocoon also predicts certain asymmetries close to the nucleus. On the windward side, where the sheath is compressed, the coma can be slightly brighter and sharper, with a faint cap that looks like a soft bow. On the leeward side, streamlines peel away, and you can see layered fans or lanes that originate from the same active patch, but are guided by different parts of the draped field. If observers catch 3i Atlas at very high resolution, especially near twilight, and when the sky is dark but seeing is steady, they might glimpse that cap and lane pattern, subtle but diagnostic. It's worth remembering we've seen cousins of this behaviour up close at other comets. Past missions flew through piled up magnetic fields, measured cavities near the nucleus, and watched the wind swerve around a comet's miniature atmosphere. Those encounters taught us that no intrinsic magnet doesn't mean no magnetic structure. It means the structure is built fresh each moment by the dance between outflowing gas and incoming wind. 3i Atlas, with its own chemistry and history, could be constructing a version of that structure that is just symmetric enough and just steady enough to fool our expectations about tail angles. There are naturally caveats. A cocoon strong enough to hold a preferred angle for hours or days implies a certain level of activity. If the total gas output inferred from brightness is too low, we have to ask whether geometry alone is doing more of the work than we think. Likewise, if the streamer shows clear signatures of dust mixed in, some of the magnetic look might be a dust sheet seen edge on, enhanced by the sheath but not defined by it. The best answers arrive when multiple techniques line up. Ion-only images, timing against space weather maps, consistent ripple speeds, and models that don't require heroic assumptions. If the cocoon picture is right, it reframes the mystery of a bent solar wind. The wind isn't being mystically repelled, it's being redirected by a structure the comet itself helps build. The tail isn't disobedient. It's a tracer of a lane that curves around an obstacle we can't see directly. And the persistence of that curve isn't an affront to physics. It's a sign that local conditions, outgassing pattern, field draping and viewing angle are teaming up to hold a line until a stronger gust of space weather redraws it. For a storyteller, that makes 3i Atlas even more compelling. We aren't just watching a rock with a tail, we're watching a tiny temporary magnetosphere breathe, swelling, tilting and flexing under the sun's breath. Each night's image becomes a diagnostic slice through that living structure. Each kink or calm patch is a clue. Follow those clues across weeks, and this cocoon either stands revealed as the quiet engineer of the bend, or it gracefully steps aside as we discover another culprit. Either way, we win, because every hour we spend puzzling over that slanted filament tightens our grasp on how a comet, a star, and a wind compose a shape out of invisible forces. Far from the sun, when most comets are still asleep, a different kind of chemistry can wake up. Not all ices are equal. Some, often called hypervolatiles, evaporate at temperatures so low that sunlight at the edge of the planetary system can already tease them into gas. Carbon monoxide is the classic culprit. Carbon dioxide can join the party. other exotica may tag along depending on the comet's history. If 3I Atlas carries a rich stash of these easy-to-stir ices, it can switch on long before the usual water-driven fireworks. That early activity matters, because when a coma builds far from the Sun, it inflates in a gentler radiation environment and grows into shapes that don't match our near-Sun habits. Jets form, yes, but they form in slow motion from deep vents, and that they keep their aim longer. The result can be narrow, persistent streamers that look like they hold steady even when the solar wind asks them to move. Think of the nucleus as a layered freezer. The topmost crust might be dusty, compacted, and reluctant to let gas out. Beneath it, pockets of super cold ice sit under tension, like carbonated water waiting to fizz. As feeble sunlight trickles in, heat creeps through the upper layers. It doesn't melt anything in the usual sense, just liberates the most eager molecules first. Gas percolates toward the surface, snaking along fractures and pores until it finds an escape route. Where those paths converge, old cracks, collapsed pits, or the rim of a sunlit depression, a jet is born. Because the gas is thin and the temperature's low, the flow can be surprisingly well collimated, a pencil-thin plume rather than a broad fan. Now add rotation. If one face of 3I Atlas spends long stretches in sunlight, a particular vent can dominate for hours at a time before slipping into dusk. That makes a searchlight jet, on for half a turn, off for half a turn, that paints a repeating arc into space. Near the Sun, water-driven outgassing can be so vigorous that dozens of weak vents blur together. Far from the Sun, a single hypervolatile vent can become the whole show. Viewed from Earth, this creates slender streamers that persist in a preferred direction for night after night, because the geometry between the Sun, the vent, and our line of sight changes slowly at large distances. The gas that escapes is neutral at first, so it isn't compelled to follow the magnetic lanes of the solar wind. It rushes out ballistically, pushing dust along the same route. Only later, minutes to hours depending on sunlight and local conditions, do photons and energetic particles strip electrons and turn some of those molecules into ions. By then, the neutral stream has already carved a path. When the ionization finally happens, it happens within a plume that began life as a directed jet. That's how a tail can inherit the stubborn aim of a vent. The ions are born inside a beam that was already laid down, and for a while they trace that beam even as the larger scale wind tries to herd them into a new direction. Dust amplifies the illusion. Hypervolatile jets are efficient at lofting fine grains because the gas accelerates in narrow channels, like steam from a nozzle. Fine dust rides that flow so closely that it becomes a tracer of the jet's shape. Unlike ions, dust doesn't care about magnetism. Sunlight and gravity govern its fate. So you can end up with a narrow dust streamer sitting almost on top of a narrow ion streamer, both issued from the same vent, but each reacting differently over time. In long exposures, they blend into a single bright filament that seems immune to the day's space weather. In reality, the ion component may be wriggling while the dust skeleton holds the line. Seasonal effects deepen the story. Even small lumpy bodies have seasons. The tilt of the spin axis sets which regions enjoy long days or long nights as the comet approaches the Sun. If a hypervolatile rich patch enters its summer, that region can feed a jet for weeks, barely changing its aim relative to the Sun. If 3I Atlas happens to present that patch toward Earth, we get a clean repeating pattern, a streamer that turns on and off with the rotation and keeps pointing more or less the same way between nights. Meanwhile, other parts of the nucleus might be quiet, either because their volatile inventory has already been drained by ancient heating or because a dust mantle insulates them. The net effect is asymmetry, a lopsided coma with a favourite direction built into it. There's also the matter of thermal lag. Subsurface ices don't respond instantly to sunrise. Heat takes time to soak into pores and reach deeper reservoirs. That creates jets that peak not at local noon on the surface, but later, when the warmth finally reaches a pocket. If a vent is on a steep wall or at the floor of a crater, shadows can modulate this timing even more. flickering the jet in a pattern that repeats each spin. The visible tail then bears a subtle pulse, bright knots spaced along the streamer like pearls on a string. Those knots aren't necessarily space weather ripples, they can be the fossilized rhythm of a vent turning on and off. From a dynamic standpoint, a focused jet can punch above its weight in the near-nucleus environment. The outward momentum concentrated in a narrow channel can sweep a clean corridor through the surrounding coma. Inside that corridor, dust and freshly released gas feel the jet's push more than the solar wind's tug. The corridor persists as long as the vent feeds it. Outside it, the coma evolves in the usual way. Ions are swept along magnetic lanes. Dust forms broader fans. When you integrate all that light along our line of sight, the corridor dominates because it's bright and concentrated, giving the impression that the tail has defied the expected direction when in truth a particular part of the flow has taken the lead. What would we expect to see if far from sun outgassing is driving the weirdness at 3I Atlas? First, activity at unexpectedly large distances, a coma present and structured when many comets would still be dormant. Photometry might show a slow, steady brightening long before water ice should be in play. Second, gas species that favour the cold, spectral hints of carbon monoxide and carbon dioxide, and a relative scarcity of the usual near-sun tracers. Third, narrow high-contrast jets that maintain shape over hours, with brightness modulations locked to a rotation period rather than to changes in the solar wind. Fourth, a mismatch between dust and ion behaviour. The dust streamer holding course while an ion-only image shows subtle kinks that the broadband picture hides. This hypothesis also predicts certain near-nucleus textures. A jet fueled by deep cold reservoirs often emerges through a specific throat. Think of a skylight in a cave roof, so the base of the streamer can look like a bright sharp-edged fan with a well-defined spine. If the nucleus rotates, that spine can sketch a spiral within the inner coma. From some angles, the spiral projects as a stack of overlapping fans. From others, it condenses into a single needle-like ray. If multiple vents come alive in the same region, say along the rim of a fractured pit, you can see parallel streamers that briefly braid together before diverging into their own paths. Those braids are not a sign of new physics. They are the signature of a complicated rock with more than one whistle in its orchestra. There are plausible triggers for the onset of such jets that don't require the comet to be unusually active overall. Microfracturing can suddenly open a channel to a deeper pocket, turning as gentle seep into a spray. A landslide along a sunlit wall can remove insulating dust and expose pristine ice. As the nucleus warms globally by a tiny amount, pressure builds under an old crust and eventually vents through the weakest spot like a punctured tyre. Each of these events can feed a jet for days or weeks, keeping a steady aim while the surrounding coma, driven by weaker sources, stays diffuse. Skepticism is healthy here. If far outgassing and jets are the explanation, the numbers should add up. The total gas output inferred from the comet's brightness must be consistent with the strength and length of the observed streamer. If the streamer is too bright and too long-lived for the available gas, other mechanisms must be helping. Magnetic draping to guide the ions, for instance, or a favourable viewing geometry that stacks many days of jet deposition along our line of sight to boost the apparent brightness. Conversely, if the measured gas favours hypervolatiles and the timing of the streamer's pulses tracks a stable rotation period, the jet hypothesis gains teeth. Observers have tools to test this without getting anywhere near the comet. Narrowband filters can isolate light from specific molecules and ions, separating the jet as seen in CO+ from the jet as seen in dust. If the far outgassing story is correct, the cold-friendly species should trace the stubborn streamer more faithfully than water family ions do early on. Time series imaging, snapshots every few minutes for hours, can search for a repeating bright dim cycle. If a rotation-linked pulse appears in the streamer, while the broader coma drifts slowly, that's a smoking gun for a vented jet. Polarimetry can map dust grain properties across the coma, a coherent zone of aligned, fine-grained scattering along the streamer, would tell us that dust rode a focused flow, not a diffuse breeze. There's a subtle consequence of early activation that's easy to miss: the development of a dust mantle. As gas escapes, it leaves heavier material behind, slowly armouring the surface. Near the sun, vigorous water activity can rip through these mantles and refresh the surface. Far out, mantle formation can be patchy and stubborn, choking most weak vents while leaving a few hearty throats open. That naturally leads to the dominance of one or two long-lived jets and an overall lopsided coma. Exactly the conditions that produce narrow, steady streamers and the "why won't that thing turn" effect on camera. All of this sits comfortably inside known comet physics. What's special is the recipe and timing. 3I Atlas, coming from another star, may carry a blend of ices with slightly different ratios than we see in many local comets. Its pores may be narrower or wider, its crust more or less compact, its fractures set in patterns laid down under a different sun. Small differences in material and structure get amplified when the primary driver of activity is something other than water. By the time water joins in closer to the sun, the jet-sculpted corridors can already be established, and for a while the new, stronger outgassing simply pours through the same lanes, reinforcing the apparent defiance. There's a beautiful feedback to contemplate. A persistent jet builds a preferred path. The preferred path focuses more gas and dust. The focused flow clears a cleaner channel. The cleaner channel keeps the jet narrow and bright. Meanwhile, the solar wind flows around the growing coma, sometimes draping its magnetic field in ways that further protect the jet's lane from being erased. It's not that the wind is powerless, it's that the comet has created a guided route for its own breath, and we happen to be watching along the line that best displays it. If this is the engine behind the odd-tailed geometry of 3I Atlas, then the story is less about a comet that bends the wind and more about a comet that learned to aim. Hypervolatile ices woke early, deep vents found their voice, rotation gave them rhythm, and the resulting jets drew luminous lines through space that our cameras mistook for stubbornness. As the comet nears the sun and the balance of ices changes, those lines may finally yield, widening into the familiar near-sun fans and arrow-straight ion tails. Or if the vents hold and the channels stay clear, we may watch the same narrow streamers carry their identity all the way through perihelion. Either way, following their evolution, what fades, what persists, what pulses, will tell us whether far from sun outgassing truly wrote the strange calligraphy we're trying to read. There's a version of this mystery where the culprit isn't exotic plasma or a new kind of comet at all. It's dust with a secret life. Dust, after all, is the quiet shapeshifter of a comet's display. It reflects sunlight like a fog, it remembers past outbursts for weeks, and it can charge up electrically so that magnetic fields and electric currents nudge it in ways our eyes don't expect. Put that dusty mischief in front of a camera, layer it along our line of sight, and it can make a perfectly ordinary solar wind look like it's being bent. In the case of 3I Atlas, this charged dust hypothesis is compelling because it explains stubborn, narrow features, odd, sunward spikes, and slow-to-change structures without asking the wind to do anything it hasn't done before. Start with how a grain of comet dust becomes more than just a speck. Sunlight knocks electrons off its surface, leaving it with a positive charge. Electrons and ions from the solar wind smack into it and tweak that charge again. When the grain slips through shadow behind cliffs on the nucleus, or into the denser parts of the coma, it can briefly charge the other way. Over minutes, a typical particle will wander through a sequence of charge states, each one altering how strongly it feels the whisper of electric and magnetic fields. Because charge scales with surface while mass scales with volume, smaller grains carry a lot more charge per unit weight. They are the gymnasts in this show, easily flipped, steered and focused, while larger grains are a stubborn furniture, drifting along mainly under sunlight and gravity. Once you admit that dust can be charged, an entire toolkit opens. The expanding gas around the nucleus doesn't shed electrons and ions at the same speed, so a natural electric field develops that points outward from the coma. That field is gentle, but it's spread across thousands of kilometers, and it can herd charged dust into lanes, squeezing a broad plume into a brighter spine. The solar wind threading past adds its own influence. Move a charged grain through a magnetic field and it drifts sideways in a way neutral dust never would. Put those effects together with a rotating nucleus that releases dust in rhythmic jets, and you can sculpt razor-thin streamers that look, to a distant observer, like somebody drew them with a stray edge. These streamers can masquerade as ion tails. In a broadband image, both dust and plasma glow, stacked on top of each other along our sight line. To the eye, a narrow, charged dust filament looks exactly like a magnetic field tracing gas beam. But there are differences in temperament. Ion beams react quickly to changes in the solar wind. Charged dust reacts slowly, or sometimes not at all, especially if the grains are on the larger end of the gymnast class. So a dust-made streamer can hold its course night after night, seeming to defy a wind that on paper should have swiveled it. Meanwhile, an actual ion tail might be quietly twisting a few degrees within that streak, but the dust's brightness overwhelms the subtle wriggle. There's another layer of deception: forward scattering. Dust doesn't shine equally in all directions. At certain angles, when we're looking almost past the comet toward the sun, tiny grains flare in brightness, like fog lit by a headlamp. A faint sheet suddenly looks like a luminous spear. If that sheet lies close to the comet's orbital plane, we get the famous anti-tail, a sunward-pointing spike that isn't breaking any rules. We just happen to be peering edge-on along a thin, dust-rich layer. Shift the Earth a bit in its orbit and the spike fades, not because physics changed, but because the spotlight moved. For 3i Atlas, a lucky alignment can amplify charged dust lanes and make them look both brighter and more defiant than they truly are. Charged dust also explains some of the most striking fine details, the ribs and beads that appear within a narrow filament. When a jet on the nucleus flickers with the comet's rotation, it sends out pulses of grains that start with similar sizes and charges. As sunlight and plasma work on them, those pulses sort themselves by size and charge to mass. The result is a series of parallel striations, like the ribs of a fan, marching tailward. Superimposed ripples can ride those ribs if the surrounding plasma shakes, but you don't need a solar storm to draw them. You just need a jet that blinks and a field that focuses. In long exposures, the ribs add texture that our brains interpret as bends and joints, even when the underlying stream is straight. Near the nucleus, electrical tricks get more personal. The innermost coma can host a photoelectron skin, a thin veil of low-energy electrons knocked off dust surfaces by sunlight. That skin creates tiny electric fences that levitate the smallest grains before letting them escape. Jets emerging through that environment can wrap dust into tight corkscrews, especially if the vent sits in a rotating rim. Seen from the side, you get a spiral. Seen from a skewed angle, you get a needle-like ray with faint, repeating bright knots. None of that requires the solar wind to do anything but blow. The architecture is built locally by light, charge, and the geometry of the vent. Composition makes the plot thicker. Dust from another planetary system may not behave exactly like dust we've catalogued closer to home. Fluffy aggregates rich in organics charge and scatter light differently than compact silicate grains. A fluffy clump carries a larger surface for the same weight, so it picks up more charge per mass and couples more strongly to electric nudges. If 3i Atlas sheds a higher fraction of such fluff, its dust lanes will be more responsive to the coma's electric fields and less eager to fall obediently into the broad sunlight-shaped fan. That's a recipe for narrow, persistent streamers that look magnetic, but are really electrical and optical. There's also fragmentation. Larger chunks break as they spin and heat, releasing clouds of finer dust that inherit the parent chunk's motion. These cloudlets can launch down previously established lanes and reinforce them, laying bright rails through the coma that persist for days. Because fragmentation is a mechanical process, not a space weather one, it doesn't care if the solar wind has tilted a few degrees. It will happily refresh the same slanted stripe we saw last night, making it seem like some invisible force is holding that line against the wind. If charged dust is behind the oddities around 3I Atlas, a few telltale behaviours should show up. First, the rebel feature should be much brighter in broadband or red filters, where dust dominates reflected light, than in narrow filters tuned to common ion emissions. Second, polarization maps, the way scattered light is oriented, should reveal dust-like signatures along the filament, distinct from the fingerprints of fluorescent gas. Third, the feature should respond lethargically to small day-to-day changes in the solar wind, yet show slow, graceful evolution tied to the comet's rotation or to our changing viewing angle. And fourth, if you watch for hours, you might see a repeating bright dim rhythm in the filament that lines up with a plausible spin period, dust being fed in pulses, while the true ion tail, isolated with the right filter, wriggles to its own faster beat. You can even predict where the charged dust wants to live. Combine two simple maps, one that says where grains of a given size end up under sunlight and gravity, and another that says how the coma's electric field focuses those sizes, and you get a set of favoured curves. Dust released at the same moment forms one family of arcs. Dust of the same size released over many moments forms another. Where those families cross, brightness piles up. Observers call these crossovers necklines, or trails, and when the Earth sits in the orbital plane, those lines collapse into sharp spikes. Add charge focusing, and the spikes narrow further. A casual glance reads them as tails choosing their own direction. A careful analysis recognizes the intersection of dusty highways. Of course, the best illusions borrow from reality. Nothing stops a genuine ion tail from running alongside a charged dust streamer. In fact, the two often share a birthplace, a persistent jet. The ion tail tries to trace the magnetic lanes. The charged dust tries to trace the electric focusing and its initial launch vector. When those paths are close together, the features merge into one gleaming filament. When they diverge by a few degrees, long exposures weld them back together. If a space weather front rolls through, the gas component might kink while the dust skeleton holds steady, producing a momentary dogleg that looks like a tail bending the wind. But it's simply two superposed stories peeling apart. Skepticism keeps this idea honest. If the bent feature stays bright in a pure ion filter, then dust isn't the main actor. If it swivels quickly with magnetic sector changes, it's not dust-led. If its colour is neutral and its polarization low, signatures typical of gas, then the charged dust case weakens. Conversely, if the feature survives aggressive gas subtraction, reddens with phase angle like dust, and carries a repeating pulse that matches a plausible rotation, the case strengthens. For 3I Atlas, a handful of well-planned nights, ion imaging, broadband imaging, polarization, and hour-long cadences can tip the scales decisively. There's a human reason this hypothesis is attractive. It leverages physics we already know, shows up in messy, beautiful ways. We have images of other comets where dust ribs stride through the tail, where anti-tails spear the sun during plane crossings, where charged grains draw filaments that only appear under certain lighting. We've watched dust trails persist long after ion tails have come and gone, like contrails lingering after a jet. 3I Atlas doesn't need to be an outlier to wear the same costume. It just needs the right blend of grains, jets, and geometry. If charged dust is doing the heavy lifting here, then the bending of the solar wind is more a trick of sculpture and spotlight than a new force. The wind still blows, the magnetic field still threads through space. Ions still respond on fast timescales. But dust, especially dust that's been quietly electrified, can build scaffolds that look like rails, and when we line up just so, those rails dominate the scene. The way forward is straightforward and elegant. Separate dust from gas with filters, watch for rotational rhythms, map polarization, and track how the feature reacts when the space weather changes. If it's dust, it will confess under that kind of interrogation. And if, after all that, the filament refuses to behave like dust or iron, if it glows in gas filters, shrugs at sector changes, laughs at rotational timing and still holds its impossible angle, then we can say with a straight face that something else is happening near 3i Atlas. Until then, charged dust remains the simplest slyest suspect. Ordinary grains, charged by ordinary light, staged by ordinary geometry, combining into a performance convincing enough to make the solar wind look like it blinked. Before you can decide whether 3i Atlas is bending the wind or just fooling us with geometry, you need the right eyes, and not just one pair. You need a chorus of instruments, each tuned to a different piece of the puzzle, all staring, timing and comparing notes. Think of it like investigating a whisper in a crowded room. The wide-field cameras tell you who's speaking, the spectrographs tell you what they're saying, the polarimeters tell you what they're wearing, and the space weather monitors tell you how loud the background music is. Starts with survey telescopes, the tireless night watch. They sweep huge swathes of sky with fast, sensitive cameras, pulling faint, moving dots out of starfields. They're built for repetition, revisit, compare, catch motion. That cadence pins down where 3i Atlas is and how it's moving night by night. The images themselves are deceptively simple, just stacks of short exposures, but the magic is in the processing. Software aligns on the comet's drift rate, rejects cosmic rays, subtracts the smeared starlight, and then stretches the faintest glows until the coma and tails pop out. If there's a skinny streamer at a strange angle, the surveys are usually the first to whisper, "Look here." Once the beacon is lit, the big glass takes over. Medium and large observatories switch from fine to understand. In direct imaging mode, astronomers play with filters like a painter's palette. Broadband filters capture everything, dust and gas together, and reveal overall structure, the broad fan, the straight spear, any narrow lanes. But broadband can be a liar, so they reach for comet narrowbands, classic filters that isolate light from specific molecules and ions. One set might highlight CN in the violet, another the C2 swan bands, another the bluish CO+, that often sketches out ion tails. With those, you can peel the scene into layers, one image that's mostly gas, one that's mostly dust. If a suspicious filament fades in an ion filter but blazes in red broadband, you've learned something critical about its nature. Spectroscopy is the voice recorder. Slit a spectrograph across the coma, and you don't just get brightness, you get fingerprints. Emission bands bloom, where active molecules flourish. Reflected sunlight makes a smooth continuum where dust dominates. By stepping the slit across the comet, observers build a crude map of chemistry. This side rich in CO+, that side richer in CN, the inner few thousand kilometers glowing with OH that betrays freshwater breakdown. On a good night, you can even measure subtle Doppler shifts that tell you which way gas is flowing along the slit, hinting at jets and outflows that imaging can't fully resolve. If a narrow eye, a rebellious streamer carries strong ion signatures, the spectrograph says so. If it looks like sunlit dust sprinkled with weak gas, it says that too. Then there's polarimetry, the stylist no one invites until the crisis. Light scattered by dust becomes polarized, its waves line up preferentially depending on grain size, shape, and composition. A polarimeter rotates its analyzer and watches the light's orientation change, turning a plain image into a map of dust properties. Broad fans often show one pattern. Narrow jet-fed streamers show another. If the impossible tail is actually dust-heavy, its polarization betrays it. If it's plasma bright, the polarization drops and the map goes quiet. Polarimetry also has a superpower at certain Sun-Comet Earth angles. Tiny grains can spike in brightness and polarization when the geometry is just right. A hallmark of forward scattering that explains sudden, dramatic spikes without invoking new physics. High time resolution imaging is the metronome. With short exposures taken every minute or two for hours, observers can watch features evolve in real time. Does a filament waggle quickly as the solar wind shifts? Eon? Does it hold steady but brighten and dim with a slow repeating rhythm? Jet plus rotation. Does a bead of brightness form near the head and march tailward, like a conveyor belt? You're seeing pulses, either from a vent turning on and off or from waves running down a plasma filament. Time series also expose disconnection events. A faint seam appears in the ion tail, a section detaches and drifts away, a fresh tail sprouts from the nucleus. When that seam is slanted rather than straight anti-sunward, the geometry of the seam itself is a clue to draped magnetic fields and local flow lanes. Adaptive optics and lucky imaging add fine brushwork. On nights of steady air, large telescopes can sharpen the inner few hundred or thousand kilometers around the nucleus. There, the base of a jet shows its spine. Spirals from a rotating vent unwind like a corkscrew, and the standoff distance, the gap between nucleus and the point where a narrow tail really takes shape, can be measured. A larger-than-expected standoff can hint at a piled-up magnetic sheath. A razor-thin spine points to a focused jet. Meanwhile, amateurs around the world, equipped with smaller but nimble gear, supply cadence no professional Q can match. Dozens of teams can monitor nightly, even hourly, filling gaps, catching outbursts and confirming that a stubborn angle isn't just a single observatory's processing quirk. Step out of the optical and the story gains new colours. In the infrared, space telescopes and ground-based instruments with sensitive spectrometers sniff for ices directly. Water hides in the infrared, so do carbon dioxide and organic bands that are otherwise hard to catch from the ground. If 3I Atlas is active far from the Sun, IR spectra can reveal which hypervolatiles are driving the show and whether a particular vent composition correlates with that persistent streamer. In the mid-infrared, the thermal glow of dust sketches grain sizes. Larger grains radiate differently than fine powder. A narrow streamer that looks dust-rich in the infrared but fades in ion images makes the charged dust case stronger. Millimeter and submillimeter radio arrays listen for the breath of molecules. Rotational lines of CO, HCN, and others pierce the radio quiet. With an interferometer's sharp ears, observers can map where gas is densest and how it flows, even separating approaching and receding components. Sometimes they'll see a jet as a velocity-split pair of blobs, proof of a directed outflow. The venerable 18cm OH lines, an old cometry workhorse, can proxy for overall water production. When production jumps but the bent feature does not respond, you learn that total activity and streamer orientation aren't handcuffed. When both change together, you learn the opposite. Ultraviolet instruments add another spare truth. UV bands pick out atomic hydrogen and oxygen produced when sunlight tears water apart, and they trace ionized carbon monoxide with clarity. For comets observed near the Sun-Earth line, UV can be brutally honest about where fresh dissociation is happening. A slanted filament bright in UV ions, but faint in dust-coloured light pulls the diagnosis toward plasma. The inverse pushes it toward dust. Even if you never get a single photon from the UV on your own scope, you can ride along on public data from solar and heliophysics missions that scan the sky in UV, catching bright comets serendipitously. None of this happens in a vacuum, figuratively or literally. Every observing plan for 3I Atlas is paired with space weather context. Monitors near Earth sample the solar wind speed, density, and magnetic field orientation. Solar imagers watch for coronal holes and eruptions. Predictive models propagate those conditions through the inner heliosphere. With that background, an observer can stamp each image with a label. Field tilted this way, wind this vast. If the filament ignores a gentle tilt but flinches at a stronger one 48 hours later, the pattern builds a case for a local structure that resists nudges and yields to shoves. Without the context, a static-looking tail could just be a calm night. With it, static becomes a statement. On the ground, the craft of measurement matters as much as the metal. Tracking a fast, faint target means the telescope must slew at the comet's exact rate. Otherwise, the inner structures smear into mush. Photometric calibration, the unglamorous ritual of turning counts into real brightness, guards against fooling yourself with processing stretches. Flat fields tame camera quirks. bias frames catch electronic noise, standard stars anchor colours. For comets, observers often take star-aligned and comet-aligned stacks both. The first preserves sharp stars to model and remove their halos, the second preserves the coma's delicate edges. Subtract the star field carefully and faint streamers emerge that would otherwise drown in stellar glow. Once the data are in hand, the analysis room becomes its own observatory. Isophoto maps, contours of equal brightness, can reveal asymmetries the eye misses. Radial profiles sliced at many angles show where one side of the coma is sharper or denser. Classic fingerprints of a windward pileup or a jet corridor. Image differencing between nights exposes features that stay put and those that drift with geometry. Even simple deconvolution, applied gently, can separate a narrow filament from a broader halo, turning a fuzzy hint into a measurable line. Coordination is where small truths become a robust story. A northern telescope catches 3-eye atlas in a twilight window. Hours later, a southern observatory picks it up under midnight skies. Amateurs fill the gap in between. The same night, a spectrograph grabs a strip. A polarimeter maps a patch. A millimeter array logs a CO line. And the solar monitors note a sector crossing en route. When all those threads are woven, contradictions either cancel or clarify. If every modality says narrow ion filament, sluggish to small field changes, realigns only when a strong disturbance arrives, the magnetic cocoon idea gains traction. If the filament lights up in dustbands, polarizes like grains, and shrugs off big space weather shifts but pulses with a rotation period, jets and charged dust take the lead. If the truth is some of each, that's fine. The instruments are there to separate blended stories, not to force a single plot. Even negative results are valuable. A night where the ion filters show nothing in the rebel direction, while the broadband image flaunts a spike as a loud dust. A night where both brighten together as a coronal mass ejection sweeps by, says plasma is in play. A stretch of days when the streamer's base crawls sunward or anti-sunward by a few hundred kilometers tells you the standoff distance is breathing with activity or with the draped field's pressure. Each small, carefully measured change is a stitch in the larger tapestry. And yes, there's room for bold experiments. Put a slit directly along the suspicious filament and step outwards to measure how line ratios change with distance. If chemistry evolves differently there than elsewhere, the filament isn't just a projection trick. Try synchronized multi-band fast imaging to watch beads propagate in different species. If the bead speeds differ between ions and dust, you're seeing two superposed rivers rather than one. Schedule observations around predicted crossings of the heliospheric current sheet. If the filament performs a dogleg exactly then, the magnetic hand is visible. All of this effort circles back to a simple promise. With enough kinds of eyes, the sky stops lying to you. 3-eye atlas isn't a single photograph, it's a performance. The wide field surveys call you to the theatre. The big mirrors bring the actors into focus. Spectrographs let you hear the lines. Polarimeters show you the costumes. Radio and infrared add the backstage view. Space weather monitors tell you when the orchestra will swell, and the people, professionals and amateurs alike, keep time, keep notes, and keep each other honest. In that ensemble, a bent-looking tale stops being a riddle and becomes a diagnosis. If it's ions tracing a draped field, the instruments will agree. If it's dust sculpted by jets and charged into rails, they'll agree on that too. And if it's a rare, delightful mixture, an early hypervolatile jet pouring down a lane protected by a modest magnetic sheath, while our viewing angle turns the whole thing into a luminous slant, the instruments are precisely how we'll know. That's the real power of these eyes on the sky. Not to declare a mystery solved in one glance, but to turn a whisper from a faint, fast visitor into a story we can tell with confidence. Line up our tiny family album of visitors from other suns, and you can already see 3 distinct personalities. One arrived like a scarred shard, sunlit but quiet. with no breath and no halo, only an odd spin and a gentle, persistent push that refused to be explained away. Another came blazing with the familiar bravado of a true comet, coughing dust and gas as if it had grown up next door. A reassuring yes to the idea that other planetary systems make snowballs too. And then there is 3I Atlas, a guess that seems to write with the solar wind itself, drawing narrow, slanted filaments and hinting that the space around a small world can be sculpted into paths and shells invisible to the eye. The first impressions shape the story. The dry drifter, we all remember how it confounded expectations. It looks star-like in images, no fuzzy coma, no tail, no obvious jets. Yet its light curve rose and fell as it tumbled, suggesting a flattened or highly elongated body turning end over end like a lost roof shingle caught in a slow gust. The active comet's debut was the opposite. Within days, telescopes saw a textbook coma bloom and a long blue ion tail lance away from the sun. Even a quick glance told you chemistry was at work. 3I Atlas starts somewhere between those extremes in the way a riddle sits between two answers. Clearly active, there's structure, there are streamers, but the geometry and timing hint at a more intricate dance between outgassing, dust and plasma than most of us have had to pass. Consider body types. The silent shard implied a surface baked or sealed. Ice is either depleted or hidden under a crust tough enough to smother obvious jets. That surface could be the result of eons of cosmic ray gardening in interstellar space, or a violent origin that baked away the frothier stuff long ago. The flamboyant comet told the opposite tale. Ices near the surface, ready to sublimate fragile grains willing to fly. It even carried a chemical accent, an abundance of cold-loving volatiles that whispered of a birthplace in a chilly nursery around another star. 3I Atlas extends the spectrum. Its activity seems focused and structured, as if ices wake early and escape through specific throats, painting the coma with fine calligraphy rather than a broad wash. If you were building a triangle of possibilities, dry shard, classic snowball, jet carved in between her, 3I Atlas drags the third corner farther out. Spin and rhythm separate them further. The tumbling shard never settled into a single clean rotation. It wobbled, a telltale of past torques and an irregular shape. The flamboyant comet likely spun more gently, with hints of periodicity and the kind of fragment-prone stress you see when jets push on a weak body. 3I Atlas feels like a metronome, its streamers brighten and thin, suggestive of jets turning on and off with rotation, laying down beads that march outward along a narrow path. Where the shard's spin was an unsolved poem and the comet's spin a quiet backbeat, 3I Atlas turns spin into choreography you can almost count. Tales tell truths, but different truths. The shard's lack of a visible ion tail was a headline. Either it was truly airless, or its outgassing hid in ways our instruments missed. It still experienced a tiny, non-gravitational nudge, sparking debates about vanishingly gentle outflows, super fluffy surfaces, or sunlight pressure on an unusually light object. The flamboyant comet's tail was everything a physicist could want. An ion spear grabbing the solar wind's magnetic lanes, dust fans sorting by size, and disconnection events that time themselves with space weather fronts. 3I Atlas adds texture to that education. Its narrow, sometimes slanted filament says the near-comet environment can set preferred lanes, through magnetic draping, charged dust focusing, or a persistent jet corridor, so that a tail becomes less a weather vane and more a guided stream. If the second visitor taught us the rulebook, 3I Atlas teaches us the footnotes. Chemistry gives each guest an accent. The shard's spectrum showed a gently reddened, featureless reflection, dust-like, dehydrated, quiet. The flamboyant comet's breath carried familiar molecules and an emphasis on the cold-friendly species that wake far from the sin, proof that another system stranded the same kinds of ices in its outskirts. 3I Atlas, in the scenes we've been sketching, looks like a blend. Cold volatiles strong enough to switch on early, yet channeled through fewer vents. Dust fine enough to charge and focus into filaments. Ions present but sometimes braided with the dust lanes so tightly that only filters and cadence can tease them apart. That compositional middle ground matters because it says the difference between dry shard and snowball is not binary. It's a spectrum set by history layering and the luck of which patch the sun sees first. Even the way each object met the solar wind hints at her planetary system politics. The shard glided through, largely as a test mass. It felt gravity, sunlight, and perhaps the faintest whisper of gas dragging from vents too thin to see. The flamboyant comet showed us the classic skirmish between an expanding coma and a streaming plasma. Bow waves, kinks, and tail cut-offs that behave by the book. 3i Atlas suggests that the book includes a chapter on small induced magnetospheres that are stronger and more asymmetric than we sometimes assume for modest comets. If a tilted, draped sheath can hold a lane for hours or days, you can build a tail that seems to prefer its own angle, until a stronger gust arrives and rewrites it in an afternoon. Origins hide in these details. The shard's shape and spin hint at violent collisional histories or long, drying sojourns. The flamboyant comet's volatile rich mix points to gentle storage in a far cold reservoir, until some billiard ball encounter kicked it free. 3i Atlas could be the wanderer that was buried deep in its home nursery's snowbank, rich in hypervolatiles and fragile structure, but later sealed in patches by mantling and microfractures so that only certain throats speak. That hybrid biography, pristine in chemistry, patchy in plumbing, matches the kind of messy planet formation stories we're now learning are common. Migrating giants, scattered planetesimals, and disks striped with temperature lines where different ices condense. What each taught us about how to look is just as important. The shard forced us to abandon the lazy idea that comet equals coma. We learned to listen for whispers, subtle brightenings, non-gravitational nudges, polarization so faint you doubt your gear. The flamboyant comet rewarded the classics. Narrowband filters, space weather timing, and the patience to watch tails snap and regrow. 3i Atlas demands a hybrid craft. It punishes single images and flat color composites. It asks for ion-only frames, for broadband to catch dust, for polarimetry to tell grains from gas, for hour-long cadences to separate rotation from wind, and for models that bring a draped field and a lopsided jet into the same frame. If the first taught humility and the second gave us confidence, the third insists on choreography. There's comfort in statistics, even when the sample size is 3. The shard says interstellar debris can be small, rigid, and quiet. The flamboyant comet says it can also be garden variety icy, with chemistry that rhymes with ours. 3i Atlas says the space between those poles is populated and interesting. That trio argues against a universe where all ejected bodies are either baked rocks or fluffy snowballs. It points instead to a continuum shaped by what layer is exposed, how deep the cracks run, and whether a chance jet can dominate the scene. The next few visitors will show us whether that continuum is smooth or clumpy, whether certain types of travellers are common because certain ejection routes in young planetary systems favour them. There are practical payoffs. Planetary defence and survey strategy benefit from knowing which interstellar objects will flare early, which will stay mute, and which will sprout narrow streamers that trick our algorithms. If 3i Atlas is the kind of object whose activity turns on far from the sun and funnels down a single lane, you can catch it earlier in ion-sensitive filters than in plain visible bands, or vice versa if dust leads. The shard told us to look for light curve quirks. The flamboyant comet told us to listen to the wind. 3i Atlas tells us to watch for lanes that hold, then suddenly let go. Even the philosophical punch lands differently, with 3i Atlas in the frame. The shard felt alien because it wouldn't behave like a comet. The flamboyant comet felt familiar because it did. 3i Atlas feels intimate because it shows us the in-between rules our own comets obey. But in a regime we rarely watch so closely, far from the sun, under gentle light, with jets that matter individually and charged dust that can draw lines across space. It's as if a traveller from another village arrives and, in the way they fold a map or tie a knot, reminds you of the technique your grandparents used, but you've forgotten to notice. Of course, comparisons sharpen when you imagine the same test thrown at all three. Point ion-only filters at the shard on its best nights. Do you see anything at all? A ghost of a streamer? Point them at the flamboyant comet and the answer is a brilliant yes. Point them at 3i Atlas and the result depends on the hour and the weather in space. Sometimes a crisp line, sometimes a dim braid woven into dust. Catch the shard's light curve for days. You get a tumbling riddle. Catch the flamboyant comets. You see outbursts and fragmentation flickers. Catch 3i Atlases and you might get a clock. A jet blinking through rotation, a lane brightening with a beat that your video's soundtrack could echo. And then, imagine rewinding each to its home. The shard, perhaps shaved from a bigger body by impact, set tumbling, dried by time. The flamboyant comet, a compacted snowball marinated in the cold, tossed out by a jostling giant. 3i Atlas, a layered fragment with cold ices in its pockets, mantled in places, cracked in others, destined to sing through one or two throats instead of a choir. Each origin story has a signature. Each signature meets our sun and writes on our sky in a different hand. The pleasure and the science is learning to read all three. If we're lucky, the next interstellar guest will land somewhere near one of these corners or draw a new corner for us. Maybe it will be a big, faint, slow rotator with a gentle coma that never quite focuses. Maybe it will be a bright, short-lived flare that disintegrates as it passes inside Earth's orbit. Maybe it will be another lane draw that confirms 3i Atlas wasn't a one-off. Whatever comes, these comparisons give us hypotheses in advance, which filters to ready, which cadences to plan, which space weather maps to watch. The shard taught us that absence can be data. The flamboyant comet taught us that familiarity can hide surprises. 3i Atlas teaches us that structure, lanes, sheaths, rhythms, can fool the eye and reveal the truth at the same time. In the end, that's the gift of holding them side by side. You start with 3 postcards from the same highway and realize they capture 3 kinds of weather. You stop asking which one is the real interstellar object and start asking which slice of the distribution did we catch this time. The shard is the whisper that says rocks get lost between stars. The flamboyant comet is the shout that says snow does too. 3i Atlas is the diagram that shows how a breath becomes a line in the wind. Together, they turn a novelty into a field of study, and your video into a story about how 3 travellers, each strange in their own way, taught us to see the space between worlds with sharper eyes. The clock is the most unforgiving instrument in astronomy, with a wanderer like 3i Atlas. The hands sweep faster than they look. Each night is a page you get to turn once, miss it, and the story continues without you. The good news is that we already know which pages matter most, because comets, interstellar or not, follow a rhythm as they fall toward the sun and swing away. First comes the slow warm-up, faint jets switching on and sketching the earliest streamers. Then the quickening, chemistry changes, dust sizes shift, and the solar wind's fingerprints become obvious in the ion tail. Near closest approach to the sun, everything tightens and speeds up. Structure sharpens, disconnections become frequent, and jets can switch from whispers to fire hoses. After the turn, the orchestra quiets. Activity fares. Lanes relax, and we read in reverse what we learned on the way in. What will finally settle the bending the wind riddle is a package of measurements we can collect across that whole arc. One piece is timing. If the narrow filament that keeps its odd angle truly comes from ions, it should pivot when the sun's magnetic field at the comet's location flips sector, or when a fast stream overtakes a slow one. If it belongs to dust, charged or otherwise, it should shrug at those changes and instead respond to the comet's own clock, brightening as a jet rotates into sunlight and dimming as it rotates out. So observers will keep running 2 clocks at once, a space weather clock that ticks with solar rotations and storms, and a spin clock that ticks with whatever rotation period 3i Atlas reveals through repeating pulses in its light curve and jet brightness. Another piece is chemistry over distance. Far from the sun, if hypervolatile ices drive the show, we expect spectral fingerprints from the cold-friendly species to dominate. Closer in, water wakes up and its breakdown products flood the coma. That transition changes the balance between dust and gas, and with it the shape and stiffness of the tails. If the slanted filament keeps its personality even as water takes over, that argues for a structural cause: magnetic draping, a jet-carved corridor, or charged dust rails, rather than just a cold chemistry effect. If, on the other hand, the filament softens into a classic anti-sunward ion spear, as water rises, the early weirdness likely belonged to the far-from-sun regime and the ions tracing different lanes. We'll also watch the standoff distance breathe, the gap between the nucleus and the point where the narrow tail narrows hardest and truly begins. That distance encodes pressure balance, outflow pushing outward, solar wind and magnetic field pushing back. If a cocoon of draped field is at work, modest swings in space weather should make that standoff edge creep inward and outward like a tide. If a focused jet is launching the streamer, the standoff might be stubborn, changing mainly with the jet's strength and the nucleus's rotation rather than with the wind. Plot that distance night by night and you get a seismograph of the comet's invisible atmosphere. Rotation itself is a test and a teacher. By measuring repeating pulses along the streamer, bright knots that march away from the head at a steady speed, we can pin down the spin period and see whether it changes. Jets act like tiny thrusters. They can spin a nucleus up or down over weeks. If 3i Atlas's period drifts while the streamer keeps pointing along a preferred lane, that suggests the lane is external, a draped field path, rather than something painted on the sky by the rotation alone. If the period stays rock steady, but the filament's brightness rises and falls like a heartbeat, the jet is likely running the show. Closer to the sun, we'll test the filament's loyalty during real space weather punches. A sector boundary crossing should tilt the ion tail like a weather vane. A coronal mass ejection should snap it, cut it, and make a fresh tail sprout. If the bent filament resists small nudges, but yields to big ones, holding its angle for days and then suddenly swinging to a new line, that's exactly the threshold behaviour you expect from a modest magnetic sheath wrapped around an active coma. If it resists even the big shoves and keeps its slant, dust has to be carrying more of the visual weight than we thought. Polarization maps and multiband imaging become the lie detectors in these scenes. Polarization high along the filament means dust is dominating the light. Polarization low means gas. Broadband images heavy and red emphasize dust. Ion-specific filters isolate plasma. Stack those results over time and you get a weather map of which physics ran the stream on which nights. Even within the gas, different ions can tell different stories. If one species clings to the slant while another follows the field obediently, we'll know the filament is a blend. Charged dust providing the bright spine, certain ions tagging along, other ions choosing the magnetic shortcuts. We'll also look for disconnection events, the moments when a seam opens across the tail and the downstream section floats away like a ribbon cut loose. The geometry of that seam matters. A straight anti-sunward cut says the field changed cleanly. A seam aligned with the filament's slanted lane says the field was already draped and the cut happened along that sheath. Catalogue a handful of these events, measure the angles and the timing against the solar wind's mood, and you can reconstruct the shape of the invisible obstacle the wind had to flow around. Dust will get its own timeline. Early on, fine grains dominate and charge easily. Later, as the comet warms, larger grains lift and carry momentum farther. Forward scattering angles will come and go as Earth's viewing geometry changes, turning faint sheets into sudden spears, the notorious anti-tail moments. If the rebellious feature blooms exactly during those alignments in broadband light, but fades in ion filters, the case for dust illusions is essentially done. If it persists outside those alignments and glows in gas bands, The dust is a supporting actor, not the star. If we're lucky with geometry, we may even squeeze out a direct sense of size and shape. High-resolution imaging near peak brightness can reveal the inner spiral of a rotating jet. From the spiral's pitch and speed, you can infer the spin. Thermal infrared data can put bounds on how big and dark the nucleus might be. And careful astrometry tracking the exact position night after night can reveal tiny non-gravitational accelerations from jet thrust. If those accelerations line up with the streamer's favoured direction, the jet explanation gains teeth. If they don't, then the streamer is less about thrust and more about the path of least resistance through the comet's induced environment. None of this happens in isolation. The observing campaign will be a relay. Wide-field surveys will keep the ephemeris tight and flag outbursts. Big mirrors will take ion-only and dust-only snapshots, run hour-long cadences, and catch disconnections. Polarimeters will map grain signatures when the phase angle cooperates. Radio arrays will listen for CO and other molecules breathing in and out, and ultraviolet instruments will mark the moment water chemistry takes the stage. Amateurs will do what they always do better than anyone: show up every clear night, fill gaps, and pounce on timing windows the big facilities can't touch. Between them all, we'll have the cadence to separate the comet's clock from the sun's. What might we learn if everything goes right? Best case 1, we watch a narrow ion filament hold a slant through small magnetic changes, ripple with speeds set by the local plasma, then finally yield and swing when a stronger gust arrives. The base of the filament sits a consistent distance from the nucleus that rises and falls with activity. Polarization stays low along the filament while dust fans out elsewhere. Models that include magnetic draping around a lopsided coma reproduce the angles and the thresholds without special pleading. In that world, the headline isn't the solar wind bends, but a modest comet can build a real asymmetric magnetized sheath that sets preferred lanes. That would tighten our theory and give us a better playbook for future visitors, and even for native comets we have misread in the past. Best case 2, the ion-only tail plays by the book, while the broadband Rebel feature flares during forward scattering geometry, pulses with the rotation period, and carries strong dust polarization. Charged grains focus into rails close to the nucleus, and then relax into a broader fan. The slanted spear turns out to be an edge-on dust sheet refreshed by a persistent jet, masquerading as a windbender only when the lighting is perfect. In that world, the headline becomes "Our eyes are easy to trick. Here's how to catch the trick in the act." That's not a disappointment. It's a skill upgrade we'll use every time a comet does something photogenic. There's also the wild card. 3i Atlas might change its own rules near the sun. Jets can shift or split, crusts can collapse, fragments can break off and briefly grow their own comae. If a chunk peels away, we'll suddenly get multiple streamers with slightly different angles and pulses. If a covering collapses, a quiet region can explode into activity, washing out the narrow lane we've been tracking and replacing it with a classic symmetric fan. Those are not failures of a hypothesis. They're chapters you can't write in advance. Watching them play out would tell us about the strength of the surface, the depth of vents, and the resilience of whatever structure has been steering the plasma. And when 3i Atlas fades into the dark, a quieter phase begins that matters just as much. Data gets stacked, aligned and cross-calibrated. Teams swap raw frames and reduction recipes to make sure a filament wasn't born in someone's software. Modelers fit the time series, rotation period, non-gravitational pushes, production rates, standoff distances against solar wind pressure. If there's a clean, repeatable relationship, say streamer angle versus predicted magnetic sector at the comet's true position, that becomes a law we can test on the next visitor. If there isn't, that becomes a warning label that some geometries are unbeatable illusions unless you use the right filters. Beyond the immediate mystery, 3i Atlas will leave a legacy. It will refine how we trigger follow-ups on interstellar candidates, which filters we prioritize at large distances, and how we schedule around predicted space weather events. It will give the citizen science community a new checklist, what to capture and when to upload so professionals can stitch a global time-lapse. It will feed directly into mission thinking too. Space agencies are studying interceptor concepts, spacecraft that loiter in ready orbits and sprint to a newly spotted interstellar object. If the lesson from 3I Atlas is that the interesting physics shows up early and in narrow streamers that will shape instruments and arrival timing for the day we chase one up close. There are no bad endings to this story, only honest ones. If the slant proves to be dust and lighting, we've sharpened our vision. If it proves to be a draped field channeling ions, we've learned how even small comets grow miniature magnetospheres that matter. If it proves to be a mix that only careful, multi-band, time-resolved work can disentangle, we've learned a method that will pay off again and again. The ticking clock is the pressure. The reward is a cleaner map of how a breath of gas, a grain of dust, and a river of plasma write luminous lines in space. And if you're watching this with a sense of awe rather than a notebook, that's perfect too, because beneath the plots and filters is a simpler truth. 3I Atlas is here and then there won't be. It came from a place we'll never see, carrying a recipe card from another kitchen in the galaxy. And for a handful of weeks it will let our sun's light and wind sketch that recipe in the sky. We get to look, to wonder, to argue, and to learn. Then it's gone, and the night remembers. If this journey into the mystery of 3I Atlas lit up your sense of wonder, stay with me. I'll keep following the clues, the pulses, the cut tails, the stubborn lanes, and I'll bring you the story they add up to. Drop your questions and theories in the comments. Tell me which explanation you're rooting for and why. If you want more deep, cozy dives into strange truths hiding in plain sight, tap subscribe and share this with the one friend who always looks up. Until next time, keep your eyes on the quiet parts of the sky. That's where the best secrets breathe.